the rule. Informally, it's written that if run S claim run R for performing an obligation, then before performing the obligation, run R should check the correlating right of run S. The correlating rights of run S, that means the obligation on run R. There is a correlating relationship between an obligation and a right. Right? This is the informal reading. And this is the formal representation. Okay. If there is a state, every formal representation here is referred to the initial stage of the system. So we can read at the initial stage, if there exists, E that means exist, F that means a future. If there exists a future state in which error has an obligation to S, that error will perform alpha.
I know that the EF basically temporal logic operator. What is O?
O is the obligation, is the model operator of an obligation. It's defined.
Yeah. So now you're mixing several logics together. What's the semantics?
That's the main thing. That's the main thing. Is the multimodal logic, and the semantic of these. All of the notation here has been defined in chapter 4 of the dissertation. What is the semantic of E, F, O, and the DON, even the DON operator, the plan, and so forth, has been defined in the dissertation.
That's where we're coming back to this is the link.
Okay.
Now, what I mentioned about transition system semantics for modal logics. And then it's not a big leap from transition systems to Petri nets.
Yeah, that's there basically.
That's what
but
we're doing
but
here.
actually, transition system is not necessary for modal logic. It's for tense logic. It's basically temporal logic.
Transition systems can serve as the formal semantics for any kind of modal logic.
Yes. Temporal logic is one type of logic that indicates change by time.
Right.
By
Yeah.
sequence.
The order. Yeah.
Yeah. There is other kind of logic. Like, for instance, in Deontic logic, the change here, what they call is about the current word and what they call the expected word. The current word and the expected word. There's also a change.
Yeah,
in the
there you have
between them.
state transition. So
That's
you have
right.
next, right? So
Right,
that's
right.
tense logic, that's tempo.
Right.
But if you say it's necessary, and so
See, transition systems,
how do you
It's-
associate
it's-
with that?
because it's a mapping, and the transition is not necessarily a temporal mapping. It's a
Right.
transition between possible worlds or states. So the modal logics to say something is possible from a state, that means you can transition to another state. And if it's necessary, that means you can transition to all the other states.
Right, right. Then when you combine these,
You have different kinds of transitions. Yeah. That's with the different modalities amount to different kinds of transitions.
okay. So basically, okay, I need to take a look, I guess.
This is, the main reference here is Van Benten, the Dutch logician.
Okay. From when?
Hmm?
From recent work? Or?
Yeah,
Very,
the main,
very recent work. In the Handbook of Modal Logic.
the Handbook of Modal Logic is just last year, or 2004, I think.
Okay, there was in the 70s or 80s.
Yeah,
there's,
but he's been around for a long time.
No. There's handbook. So this is a revision of that, or a new one?
This is the new Handbook of Modal Logic. It's an edited work.
Okay.
You know, modal logicians, a dozen different
Right,
modal
right.
logicians, and
Yeah.
but
Okay.
you just look on the internet. It's out. And some of the chapters, not all of them. Some of the chapters are free on the internet. So.
Okay. So let's give you again the context until now. Here is about the contribution of the research. I explained already the contribution. The first contribution is a formalism. That's called Deontic Petri nets for modeling the Deontic process. The second is a ways or a method to analyze the Deontic process to identify control principles. And the third contribution that I try to explain here is the formalization of the control rules in formal logic. Here, specifically is on the combination of various modal logic, including temporal logic, Deontic logic, and the logic of action. look here, done, do is the logic of action. And another contribution, the last contribution of the research is the working prototype. And I have a demonstration session about the working prototype. If we have time, we go there briefly to see how it works. But the prototype implementing the standard Prolog, more specifically in the GI Prolog, the Java interface Prolog, developed by Jericho in 2008. Actually, it's for a long time before, but the new release is in 2008. The program is based on the technical model checking developed by Nilsson and Marsat in the year 2000. But this kind of technique has been developed for the state transition graph. What I do here is I modify the algorithm a little bit to work with FetriNet, and I combine certain operator like non or do operator and so forth. The detailed explanation of what I do with the program has been explained, I think it's in chapter 7. And the second thing is that a program that gets the result from model checking and generate the control requirement. The advantages of the approach compared to other approach in the automatic analysis of control is that I try to maintain the theoretical rigor of the representation and the plausibility and extensibility of the implementation. So in this approach, if you can model, if you can describe a control principle in the form that I provided before, including a temporal formula and a control obligation, then you can add into the system without modifying the program. This is the key issue. Yes, all of the components of the program have been defined rigorously. The algorithm, I provide the semantic of the algorithm in chapter 7 of the dissertation. The validation, I validate the result in 3 criteria. The first criteria is the theoretical rigor of the result. For every component, for every notation used in the dissertation, I provide the formal syntax and formal semantic. And then the computability, as I just told you, a control rule can be implemented naturally